Hello again, I'm Chad McMillan. I had the honor of working with Justin Astalos for these last 6 weeks. It's been an honor and a pleasure. And today he's going to be talking to us about association data mining using Apriori.
This is a joint work with Dean Zeller. There we go. Okay, so before we get into data mining, we have to talk about what very large data sets are. Basically, very large data sets are exactly what they sound like, very large data sets. So, the amount of data that is in existence has increased exponentially over the last few decades. And at this point in time, it's gone to where it's relatively difficult to handle. Between Amazon, Google, Microsoft, and Facebook, there is 1,200 petabytes of stored data. For those of you that don't know, a petabyte is 1,000 terabytes. So when we were at Seagate and everyone freaked out over those little 2 terabyte hard drives, well, there's actually 600,000 of those just between 4 big companies. This one. There we go. Okay, so some examples of very large data sets. On average, Facebook has 2 billion, 190 million active users. And active users are just users that have signed in within the last 30 days. So between a quarter of the world's population, you can imagine that they have a lot of data that they're producing constantly. Also, in the last year, Amazon has had 30 billion visits to their website and $178 billion in sales. So you can imagine there's a lot of transactions that go into that data. Seems harder than it looks. Okay, so first, a quote by Everett Dickerson. A billion here, a billion there, and pretty soon you're talking about real money. So this quote emphasizes how millions are really obsolete at this point. You really have to get to billions and even trillions before you're talking about things that still matter, especially when you're talking about data. And now, a quote from Dean Zeller. A petabyte here, a petabyte there, and pretty soon you're talking about real storage space. So, thank you, Dean. Okay, so now, what is data mining? Basically, data mining is how we analyze these very large data sets. It includes special algorithms that are much more efficient with large data sets than traditional algorithms are. Excuse me. Traditional algorithms go through much more data and thus take a lot longer time to compute, which makes them obsolete in the cases of very large data sets. So now we're getting to my example. The first thing here is brute force algorithms. So here I have a bucket of sand. In this bucket, I estimate that I have between 100,000 and a million grains of sand. These are used to represent data points. So in a brute force algorithm, I would go through, and if I have a valuable piece of data I'm looking for, such as this penny, in this data set, I would go through and I would pick, and I would check to see every single grain of sand to see if it's the penny. So, is this the penny? No, it's not. Is this the penny? Nope. 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 On and on and on through all of the grains of sand until I found the penny. Now, obviously, this is very ineffective. It takes a long time to compute. However, the solution is easy to program just because all you have to do is program it to tell it to look. So, while this is easy and a relatively beginner solution to these problems, it takes a long time and is not effective. So, the next, a more effective way to do these things is with something called a traditional algorithm. Now, this is a step up from a brute force algorithm. A traditional algorithm uses logic to find this same data. So in the same problem, I have this strainer. Now this is like my logic. I can scoop through more data and use logic to figure out more quickly if it's the data that I'm looking for. So I can scoop here and see that it's not the data I'm looking for, and scoop here. And I would have to scoop a lot of times, but eventually I would find this penny. Now, because this bucket most likely does not have billions of grains of sand in it, you would have to imagine roughly 1,000 times this. So like, if I had a bucket the size of this table, completely filled with sand, maybe like 10 or 15 of those with this. So again, not very effective, but it is more effective than brute force. Now, something like this is not possible for all problems because there's not always just a piece of logic that you can use to solve the problem. But it does do the job for most problems, and it works in our situation. So what we're really talking about here is data mining algorithms. Now, these use a traditional piece of logic, but they incorporate something different. So, for example, if I have, again, my bucket of sand, and I have this, a metal detector, right? So I can go over it, and I can see, beep, okay, I know that my data that I'm looking for is somewhere in here. I can go over it again, beep, and I know that it's somewhere right in here, right? So now I can scoop relatively efficiently. Okay, I didn't get it that time. Okay, I didn't get it that time. But here, on the third time, I got it. And I did not have to sift through billions and billions of data points or grains of sand to find the results that I'm looking for. So this, in essence, is what data mining algorithms do. They use a mining approach, so only going for the things that they want to find and ignoring all of the other data. And it eliminates everything that it doesn't want very quickly, and that's what makes it efficient. So, Apriori is an example of a data mining algorithm. Apriori uses frequent combinations or frequent items to find frequent combinations. So basically, if you have a lot of frequent items, or if you have an item that appears frequently, it is likely to appear frequently in combination. And this method is efficient because of what is called data pruning, which I will explain in a little bit. First, a little bit of history on Apriori. It was created in 1994 by these two guys. This is Rakesh Agrawal, and this is, oh gosh, Ramakrishanan Sirpant. And they created this algorithm because at that point in time, data sets were becoming large enough to where they needed a more efficient way to analyze them than just traditional algorithms. So, to exemplify exactly what it is they did, I'm going to provide an example. Apriori is particularly useful for transaction databases because what it finds is frequent combinations. So for example, if I went to the store and I was to have a transaction. So let's say for transaction 1, I bought lettuce and beer and diapers. I wouldn't buy diapers because I'm not 21. But in theory, if I were to buy those, then Apriori would find the connections between these. So given this simple 6-transaction database, I can find all of the different combinations here. So in this database, there actually is built in an association rule. But just by looking at this, it's relatively difficult to find. So Apriori does a step that makes it a little bit easier. The first thing it does is it counts up how many times each item was purchased. So, for example, lettuce was purchased 3 times, beer 3 times, basketball 2 times, you get the idea. And this is what Apriori finds before data pruning, which is what I was going over earlier. And then it goes through data pruning and it spits out this other chart, which does not look that different. But what it has done is it has removed light bulbs, which were only purchased once. Therefore, it is very unlikely that they appeared in combinations as well. So, to explain a little bit more about why it uses data pruning and why that's so effective, I'll explain it. So basically, to give a definition, data pruning is going through all of the data and finding the items that do not occur frequently and then removing them. So the fact that they don't occur frequently means that we don't really need them. So like this guy here, trimming his tree, if you were trying to count, say, all of the leaves on the tree and find a golden apple, and you know that the golden apple is not on this branch, you could cut off that branch and not have to look through that part of the data, and thus data pruning. So if you have, for example, 5 items, soup, lettuce, milk, cookies, and cereal, then you have 5 items, and there are 10 different ways that you could combine those items. So for example, this would be a combination of soup and lettuce, and soup and milk, and soup and cookies, so on. And there are 10 ways to combine 3 of them. And there are 5 ways to combine 4 of them. So when you get through this, this looks relatively complicated. And this is only with 5 items. However, when you go through data pruning, if we add numbers to these to see which transactions are the ones that we really want, if we look at the numbers, we can see soup was purchased 23 times, lettuce 19 times, milk only 3 times, cookies 27 times, and cereal 28 times. So it's like this is a market in a vegan neighborhood. Nobody really wanted the milk. So we can take that out, and you can see it actually highlights a lot of different combinations. And since milk doesn't appear frequently, you can assume that those combinations also do not appear frequently. Thus, we could just take them out. This leaves a much smaller data set and a much less complex data set to be analyzed. And actually, the number of combinations that are within this data set are actually 50% less. There's 50% less combinations in this data set than the one before, which can be proved by Pascal's triangle. Okay, so coming back to our a priori example, after we have gone through data pruning, this chart actually has 50% less ways to combine all of the items on it. So it returns this chart, which shows how many different ways, or it shows how many times each combination appeared. So, for example, lettuce and beer were purchased together 1 time, and lettuce and diapers were purchased together 1 time. Now, the one thing that may seem a little bit surprising on here, diapers and beer were purchased together 3 times. This was an actual phenomenon that was observed by running an a priori algorithm on a data set. As observed by Forbes, the diaper beer syndrome occurs very frequently. It turns out that new parents actually, when they're going to get diapers, they're real stressed and they're like, hey, I could use some of that. And grab some beer. So, obviously not an expected result, but it is something interesting that comes up out of a priori and marketers could use to their advantage. So, I built an algorithm that kind of follows the same sort of steps. So the first thing I did was I made a function called search data, which finds how many times a certain target number appears within a data set. So it starts with a variable called counter that is set to 0, and then it searches all the data, and every time that the data is equal to the target number, it adds 1 to the counter, and at the end returns the counter, thus how many times that number appeared. So the next thing I did after this was I ran this function multiple times for every number within the data set. That way I would know how many times each number occurred, and thus performing the first step of a priori. So to be able to do that, though, I needed to be able to know what the highest and lowest numbers within the data set were, so that it didn't just run that search, whatever that was called, an infinite amount of times. So first, find highest, it just sets a high number at 0, and then every time it finds a number that's higher than it, it sets high equal to that number until it has gone through the whole data set. And the same thing with lowest. And that way it can find the highest and lowest numbers within the data set. And something that should be noted at this point is that both this function and my previous function use brute force methods. As a reminder, this is where you're picking through every single grain of sand. So in a real a priori algorithm, this would only be performed on a small sample from the larger data set to find these association rules, which you could then apply to the entire data set and then run the algorithm in a reasonable amount of time. So the next function that I made was called factorial list, and it finds all of the possible combinations within each transaction. So, for example, it would be put in a transaction 1, 3, and 4. So if I bought milk, lettuce, and cookies, then it would return as a combination. You could associate milk and lettuce, milk and cookies, or lettuce and cookies. So that's what this function does with all of the different items within the transaction. And then this function, calculate matrix, just takes the results from factorial list and runs it on every single transaction within the database, and then makes a matrix or a chart showing which combinations were found and how many times they were found. So, results and discussion. Okay, because the algorithm that I created was a brute force algorithm, I could not run it on a large data set because it would be very inefficient and it would take a lot longer than 6 weeks to figure out any sort of reasonable combination. So instead, I just plugged in different numbers for so like how many transactions and how many items per transaction, and timed it to see what it looks like. So here I increased the number of transactions incrementally by a power of 10, and the time also increased by a power of 10. So from 1,000 to 10,000 to 100,000 to a million, and then the time went from 0.02 seconds to 0.25 to 2.55 to 24.96. So this showed linear growth. As I increased transactions linearly, I also increased the amount of time it took to calculate all of the combinations linearly. When I increased the number of items per transaction, it showed exponential growth. This meant that as I increased, in each one of these, I doubled the number of items per transaction, and the total time that it took to find all of the combinations more than doubled. So it was growing exponentially. So in the future, because I did not include a data pruning algorithm or a data pruning function within my algorithm, I would like to be able to implement that. This would increase the efficiency overall of my algorithm and thus allow me to apply it to real data sets. So I could find some real results, such as that diapers and beer are associated. So I would like to first acknowledge Dean Zeller for all the help that he gave me. He guided me through this research, and it would not have been possible without him. Also, Taylor McMillan, he helped me with the presentation, with the paper. So the research process, really I can accredit to him. Also, the Adolf Coors Foundation and the Bacon Family Foundation, I would not have been able to attend this program without their financial support. So if you're watching, thank you. Also, the University of Northern Colorado, thank you for letting us use your facilities. We all appreciate this experience that you've been able to grant us with your facilities. Also, Lori Ball, thank you for putting all of this together. It means a lot to all of us. This is an incredible experience that we could not have without your help. And last of all, the staff of the Frontiers of Science Institute. You guys all the teachers, you taught excellent classes. Jaden and Michael, you guys were excellent to us. And thank you everyone else for helping put everything together. So yeah, these are my references. Are there any questions? Okay.
You didn't say necessarily, but your code looked like it was Python.
Yes.
So is there any advantage to using Python, say, over Java, or is that more a personal preference?
It is more personal preference. It's just which kind of code that you have experience with, and thus you could apply in the most efficient way, basically. Amy.
What languages do companies like Amazon?
That, I could guess, I don't know for sure, but my guess is they use more basic languages like C++, just because Python is a relatively layered language. There's more built-in functions. My guess is they use C++ or something like that.
Does that increase efficiency?
Kind of, not really, but a little bit. They might have built their own things. Lance.
How long are typical lines of code for a program like yours versus a program like a data mining program?
It can vary. The most efficient algorithms sometimes are the shortest ones, sometimes are longer. It really depends. It's more the way that it's applied and how many times you have to run a certain amount of code. So even if I had 4 lines but I ran it 1,000,000 times, it would be worse than if I had 100 lines but I only ran it 10 times. So
what would be the difference in code for what you're doing now, like doing?
I'm sorry, could you repeat the question?
Like what would be the difference in code from like the brute force right now and what you're doing?
Okay, so I haven't been repeating the questions, I apologize. What she asked, what is the difference between a brute force algorithm and a traditional algorithm? So exactly what is this logic? Basically, this is sort of like data pruning. It can go through the data and decide more quickly whether it's data that is being useful, whether it's going in and finding a sample size, a small sample before, and then deciding to discount a small part of the data or something like that. I can't think of any specific examples, but it's logic like that.
How do you deal with error in these algorithms? Because like when you're trying to cancel out, right, stuff that doesn't make sense, like you did with milk. Right? How do you deal with error in case that's getting rid of usable data?
Well, okay, so he asked, how do we account for error in if we canceled out something that might actually have a useful application? During the data pruning process, we kind of assume a lot that we don't, we're not going to find any useful trends or useful combinations, because if you find a combination that doesn't have a lot of items, it doesn't have a lot of items, then you can assume it's not going to have a lot of combinations, which really, this is mainly used for like marketing and things like that, and you don't really want to market something that isn't popular, if that makes sense.
So is Apriori like a specific algorithm for like transactions as you showed us, or could it be used in other?
Okay, the question was, can Apriori be used outside of transactions? Yes. Yeah, it just associates 2 things, and that is particularly useful for transactions, but it can be useful for other things that might end up being related. I can't think of any specific examples, but yeah, it can be used outside of transactions. Any other questions?
Thank our speaker.